everyone, welcome back to the Comptia Network Plus course, Encryption. Sometimes, like it or not, sending out corporate, financial and other types of sensitive data over the internet just can't be avoided. This is why being able to hide or encode the data with encryption technologies is so vital for shielding it from the prying eyes of a company's competitor. Identity thieves, anyone who wants to take a look. Without encryption, our sensitive files and information are essentially being paraded on full display as data courses over the internet. Encryption works by running the data, which is encoded, is represented as numbers, through a special encryption formula called a key that the designed sending and receiving devices both know. When encrypted data arrives at its specified destination, the receiving device uses that key to decode the data into its original format. Back in 1979, the National Security Agency, NSA, classified encryption tools and their associated formulas as munitions, and the NSA has overseen their regulation ever since. The dangerous possibility that hostile nations, terrorists and criminals may use encrypted communications to plan crimes and go undetected is the compelling reason for doing so. It's also the reason that we're allowed to export weak encryption methods. This brings up a question: exactly how do we measure an encryption algorithm's methods? This brings up an important question. Exactly how do we measure an encryption algorithm's strength? One way we do that is bit strength. Until 1998, only software with 48-bit strength or less could be exported, but today that has been raised to 64-bit. And by the way, exporting any software with a key length greater than 64 bits to review by the Export Administration Regulations EAR, required by the US Department of Commerce Bureau of Industry and Security. This doesn't include exporting to every country because some, like most in those Western Europe plus Canada, Australia, Japan, are countries we trust with the technology. But if you happen to be curious or just want to reply carefully, check out the current registrations at www.bis.doc/index.php/regulations-EAR. Remember, these regulations aren't there to make life a hassle. They're in place to protect us. The greater number of bits that are encrypted, the tougher it is to crack the code. Encrypting passwords being sent from a workstation to a server at login is the most basic need for internal networks, and it's done automatically by most network operating systems today. But legacy utilities like File Transfer Protocol, FTP and Telnet don't have the ability to encrypt passwords. Most email systems also give users the option to encrypt individual or all email messages. And third-party software packages like Pretty Good Privacy PGP are used by email systems that don't come with encryption abilities of their own. And you already know how critical encryption is for data transmission over VPNs. Last but not least, encryption is clearly very important for e-commerce transactions, online banking and investing. Symmetric encryption keys. Using symmetrical key encryption, both the sender and the receiver have the same key and use it to encrypt and decrypt all messages. The downside of this technique is that it becomes hard to maintain the security of the key. When the key at each end are different, it's called asymmetrical or public key. We'll talk about that right after we discuss some encryption standards. The Data Encryption Standard, DES. Kudos to IBM for coming up with one of the most widely used standards. Data Encryption Standard, DES. It was made a standard back in 1977 by the US government. If you want, you can look it up in the Federal Information Process Standards publication 46/2 FIPS 46.2. Basically, DES uses lookup and table functions, and it actually works much faster than more complex systems. It uses 56-bit keys. RSA Data Systems once issued a challenge to see if anyone could break the key. A group of internet users worked together to attempt this task, with each member dealing with a portion of the 72 quadrillion possible combinations. They succeeded and cracked the key in June 1997 after searching only 18 quadrillion keys. They're surprised, knowing that they had succeeded, when they read a plain text message that said, "Strong cryptography makes the world a safer place." Back in the day, DES was a great security standard, but its 56-bit key strength had proved to be too short. As I said, the key was first cracked in June 1997. A year later, one was cracked in just 56 hours. And in January, a DES key was broken in a blazing 22 hours and 15 minutes. Not exactly sure why. We're definitely needed something stronger. Triple Data Encryption Standard, 3DES. That's when Triple Data Encryption Standard 3DES, also referred to as TDES, came into its glory. Originally developed in the late 1970s, it became a recommended method of implementing DES encryption in 1999. As its name implies, 3DES essentially 3 DES encryption methods combined into one. So 3DES encrypts 3 times, and it allows us to use 1, 2 or 3 separate keys. Clearly, going with only one key is the most secure, and opting to use all 3 keys gives you the highest level of security. 3-key TDES has a key length of 168 bits, 56 times 3, but due to a complex type of attack known as meet in the middle, it really provides only 112 bits of security. It gets worse farther down the food chain, even though the 2-key version has a key size of 112 bits. It actually arms you with only 80 bits of effective security. Another problem with 3DES is that it's slow. No one likes that, so the National Institute of Standards and Technology, NIST, believes that 3DES will be an ineffective encryption standard only until around 2030. Even now, it's being phased out in favour of faster methods like AES. The Advanced Encryption Standard. The Advanced Encryption Standard, AES, also known as RINDEL, has been the official encryption shared in the United States since 2002. It specifies key lengths of 128, 192 and 256 bits. The US government has determined that 128-bit security is adequate for things like secure transactions and all materials deemed secret, but all top secret information must be encoded using 192 or 256-bit keys. The good news is that AES standard has proven amazingly difficult to crack. Those who try to use a popular method involving known as a side channel attack. This means that instead of going after the cipher directly, they attempt to gather information they want from physical implementation of a security system. Hackers attempt to use power consumption, electromagnetic leak or timing information like the number of processor cycles to complete the encryption process to give them critical clues about how to break the AES system. Although it's true, the attacks like these are possible to pull off, they're not really practical to clinch over the internet. Public key encryption. Public key encryption uses the Diffie-Hellman algorithm, which implies a public key and a private key to encrypt and decrypt data. This is called asymmetric encryption. It works like this. The sending machine public key is used to encrypt a message that is decrypted by the receiving machine with its private key. It's a one-way communication, but if the receiver wants to send a return message, it does so by the same process. If the original sender doesn't have a public key, the message can still be sent with a digital certificate that's often called a digital ID, which verifies the sender of the message. Figure 13.8 shows public key encrypted communication between user X and user Y. RSA Data Security. Rivest, Shalmir and Edelman. RSA Encryption is a public key algorithm named after the three scientists from MIT who created it. They formed a commercial company in 1977 to develop asymmetric keys and nailed several US patents. Their encryption software is used today in electronic commerce protocols. Pretty good privacy. In the early 1990s, Phil Zimmermann, also from MIT, wrote most of the code for this freely available version of public key encryption designed to encrypt data for email transmission. Zimmermann basically compared email to postcards because anyone can read email messages traversing the internet just as they can post cards travelling through the postal service. By contrast, he compared the encryption message to a letter mailed inside an envelope. Figure 13.9 shows the PPPoE encryption system. In figure 13.9, the document is encrypted with a session key, which is then encrypted with the public key of the recipient. Then the ciphertext and the encrypted session key are sent to the recipient. Since the recipient is the only person with the matching private key, only they can decrypt the session key and then use it to decrypt the document. Zimmermann distributed the software for personal use only, and as the name implies, it's a pretty good security. RSA Data Security and the US federal government both had a problem with Zimmermann's product. The RSA complained about patent infringement, and the government actually decided to prosecute Zimmermann for exporting munitions-grade software. The government eventually dropped the charges, and now a licensing fee is paid to RSA. So today, PGP and other public key related products are readily available. Remote access. Think of remote access as a telecommuting tool because it's used by companies to allow remote employees to connect to the internal network and access resources that are in the office. Remote access is great for users who work from home or travel frequently, but clearly to a stalking hacker, using an unsecure remote access connection is like stealing candy from a baby. Using remote access requires a server configured to accept incoming calls and also requires remote access software to be installed on the client. Microsoft Windows operating since Windows 95 have had remote access client software built in, and there are many third-party remote access clients available today. Several different methods exist to create remote access connections. RES, Remote Access Service, is not a protocol but refers to a combination of hardware and software required to make a remote access connection. The term was popularized by Microsoft when the company began referring to its Windows NT-based remote access tools by this name. Users would dial in via a modem, be authenticated by the server, and then ask for their username and password just as if they were on the local network. Once logged in, users had access to the internal network just as if they were logged in locally. Figure 1310 gives you an idea of what it would look like. RES itself was not secure, but there were options within RES to include a secure protocol for tunneling, such as point-to-point tunneling protocol, and for authentication, such as Microsoft Challenge Handshake Authentication Protocol (MS-CHAP) and Extensible Authentication Protocol (EAP). RES is versatile because it supports several other network protocols in addition to TCP/IP. Rdp, Remote Desktop Protocols, allows users to connect to a computer running Microsoft's remote desktop services, but a remote computer must have the right kind of client software installed for this to happen. Most Windows-based operating systems include an Rdp client, and so do most other major operating systems like Linux, Solaris and Mac OS X. Microsoft's Rdp Client Software is called either Remote Desktop Connection (RDC) or Terminal Service Client (TSC). Microsoft began calling all terminal services products Remote Desktop with Windows Server 2008 R2. Rdp uses TCP port 3389. After establishing a connection, the user sees a terminal window that's basically a pre-configured window that looks like a Windows desktop or another operating system's desktop. From there, the user on the client computer can access applications and files available to them by using the remote desktop. The most current version of Rdp is Rdp 10.0. When logged in using Rdp, clients are able to access local files and printers from a remote desktop just as if they were logged into the network. Rdp offers 128-bit encryption using the RSA encryption algorithm and also offers TLS 1.0 support. Point-to-point protocol PPP is a layer 2 protocol that provides authentication, encryption and compression services to clients logging in remotely. ISPs use PPP a lot to authenticate clients dialing in with a dial-up modem or a DSL or cable modem. Many network servers that provide remote access services such as RES can also use PPP as an authentication protocol. PPPoE, point-to-point protocol over Ethernet, is an extension of PPP. Its purpose is to encapsulate PPP frames within Ethernet frames. The need for PPPoE was born out of the need to deal with massive increase in high-speed internet connections. Service providers offering customers high-speed access using asymmetric digital subscriber ADSL or cable modems needed a way to offer the authentication and encryption services of PPP. A remote authentication dialing user service, Radius server, something I'll get into a bit later in this chapter, is commonly used to manage point-to-point protocol over Ethernet connections. PPPoE works in two stages: discovery and session. In the discovery phase, the MAC address of the endpoints are exchanged so that a secure PPP connection can be made. During this phase, a session ID is also created that's used to facilitate further data transmission during the session. Then a point-to-point connection is created when a session stage begins. So I'm going to leave it here today for this video. If you like listening, please consider like, share and subscribe. Thank you.